So now we need to be able to predict when we're going to have turbulent flow because it is very different from laminar flow. And the relationships that we've developed in the last few lectures don't work if the flow has become turbulent. So we need to know when that happens. As I've said, viscosity decreases the tendency of the flow to be turbulent. Viscosity is a stabilizing influence. Sticky fluid is less likely to exhibit turbulent behavior because spinning and swirling is inhibited by the fact it sticks to each other, it sticks to itself. Inertia, on the other hand, promotes turbulence. So things that are the inertial forces pushing from behind or pushing from below tend to cause turbulence to occur. So this is the scale. If you just looked at the x momentum equation, for instance, we know the scale for the inertial terms. They come out of this term rho u du dx. And then we saw when we did scale analysis that these inertial terms actually all had the same size. And the scale for these can be written as rho u infinity squared over L. Remember, so we've got u infinity, L is the length scale on the bottom, and rho. So that's our rough scale for inertia. And then viscosity comes out of these second derivative terms where we have mu, the viscosity, times the second derivative. And we saw that the scale for that can be written as u mu u infinity over L squared. So if we say that turbulence is actually a function of the ratio of these two forces, so we have inertia over viscosity. And if the inertial scale gets high relative to the viscous scale, that's when we're going to have turbulence. So we're going to look at the inertial scale, rho u infinity squared over L, and divide that by the viscosity force scale, rho mu u infinity over L squared. And when we do that, you can see that the one L is going to cancel this, one u infinity is going to cancel that. And so I end up with that this ratio is equal to rho u infinity, and then in the bottom I have mu over L. So that L is going to come up on top. So the ratio that I'm looking at here is equal to rho u infinity L over mu. But this mu and this rho I can multiply up and down by 1 over rho, and I get u infinity L over nu. And that hopefully you recognize now, because we've been playing with this quite a bit. That is your Reynolds number based on L. So one of the reasons the Reynolds number is so important in fluid mechanics, it is a direct measurement of the ratio of inertial forces to viscous forces and the forces in the flow. And the Reynolds number, therefore, is going to determine whether or not a flow becomes turbulent. For flow in a pipe, there's a very clear number. So for large Reynolds numbers, you have turbulence. But the question is how large is large? Well, for flow in a pipe, you get turbulence if the Reynolds number based on the diameter of the pipe is greater than 2,000. So that's kind of a magic number that you need to remember. So if the Reynolds number is greater than 2,000 only for flow in a pipe, but for flow in a pipe, a Reynolds number of greater than 2,000 means that turbulence will occur. When you have turbulence decreases the entrance length. The flow becomes more fully developed more quickly in a turbulent situation. So it's a very simple relationship. The entrance length for turbulent flow is just equal to approximately 10 times the pipe diameter. That's it. So this is for turbulence. Turbulent pipe flow. So in pipe flow, some people don't even think there is an entrance length for turbulent pipe flow. They say there is none. There actually is one, but it's only 10 pipe diameters. If you have turbulent pipe flow, and you want to calculate the resistance, you can no longer do it by solving the PDEs. It's just impossible. So the way you can do it, you can use it actually with a supercomputer, but not by hand. So the way that engineers actually find resistance to flow when you're dealing with turbulent pipe flow, they use something called the friction factor. And the friction factor is something that we're going to be able to calculate based on some conditions in the flow. But the definition of the friction factor is it's 8 times the wall shear stress divided by rho u squared, where u is the average velocity. So this is important. You're going to need this because this is going to let you calculate resistance, going to let you calculate wall shear stress for a flow in a turbulent pipe. So when we have a turbulent pipe, you're going to have to find a way to get this friction factor, and then you're going to be able to calculate pressure drops and flow rates based on the flow situation you have. And we'll talk about how to calculate friction factors in the next set of lectures.